We start? Yes.
So if in a given material we see a superconductivity is realized with electron-photon interactions, does it mean that we can be at too low a temperature to be in a superconducting regime, or is at all temperatures below Tc we're going to have superconductivity?
So at all temperatures below Tc, you will have superconducting phase, unless at very low temperatures something happens that we don't know yet, like some other phase appears. But for most materials, we see that they become superconductors at Tc and they remain superconducting. So what you can think of is you don't really, so at low temperatures, there are no excitations in the system. So one would think that, I guess you're trying to say if there are no phonons, how come there is some attraction? So what you can think of is the following, that you don't really need phonons for this attraction. You have an electron with K. This electron will emit a phonon, and this phonon will get absorbed by the other electron. So you don't need to start with phonons to have this mechanism. Another way to think of it, like how this really happens, is a cartoon picture, but there are limits to which you should apply this picture to, but I'm going to try to convince you that this interaction can happen without any other phonons present. So imagine that you have some ions, so positively charged ions, and they are connected with springs. To a bunch of other ions also in plane above and below the board. Now consider this electron, one single electron moving through the system. If this electron, say this electron happens to be here at some time instant t. At that time instant, these neighboring ions are going to see this charge density and will respond to this charge density. What will be their response? Their response will be that, let me just try to show it here. The response would be that this charge will effectively come here So is the figure clear? What we are saying is we started at some time instant t, an electron there, and because of just from Coulomb interaction, we would expect these positive ions to respond to this negative charge density, and they will move slightly. This will create an excitation which we are trying to show here as a phonon. Now, electrons are mobile in this system. In fact, we calculated their velocity. Their velocity is given by the Fermi velocity. So these electrons are really moving with velocity, Fermi velocity, which is quite high. So Fermi energy is very large, Fermi momentum is very large, Fermi velocity is typically a very large number. So this electron is really fast, while ions are very slow. So at some given time instant t, the ions saw this negative charge and are responding to it, but ions move very slowly. So they will respond to it very slowly, but by the time they respond or they are deflected, this electron is long gone. This electron is really moving very fast. As a result, what you are left with is some positive charge density. Now, another electron at near Fermi C, will see this positive charge density and will get attracted towards it. So both electrons. So this is how you can think of attraction between electrons mediated by phonons, which are excitations of vibrations of the ion. So what you really need, so two electrons are never there at the same time. In fact, this interaction is retarded in time. And the second thing that you should note is all you need is lattice vibrations. So there need not be any excitation to begin with, but the fact that this electron can create an excitation, that's important. So you do need presence of a lattice or the ability to excite phonons.
So with that, you have like a cartoon picture of the Cooper pair, because that electron that moves leaves like a halo of positive charge. So you have another one that's following that. Is it like that cartoon picture?
So when you talk about a Cooper pair as an object, so this is the mechanism, but you really should talk about this pair wave function.
Okay.
And this pair wave function, so what happens, this is again the mechanism that provides attraction. And as a result of this mechanism, you can think of electrons as paired objects. And then all of these electrons pair up. And then in the end, the superconductor, all of these Cooper pairs, which are bosons, they condense in the same ground state. So the wave function for one Cooper pair is same as wave function for all other Cooper pairs. In fact, all of electrons are described by a macroscopic wave function now. But this is the mechanism that gives rise to an instability in the system. So if you cannot excite phonons, so let's say we can excite phonons, and due to this mechanism, below Tc or at Tc, there is an instability in the system. And what does this instability say? This instability says that electrons can actually pair up with this mechanism. And as a response, so what happens at this temperature? Due to this instability, the system tries to minimize its free energy. And then the system undergoes a phase transition. And in this phase, this new phase, superconductor, we have Cooper pairs. So this is what triggers the phase transition. Yes?
There's another question. Is it fair to think of logarithmic excitations as excitations that destroy superpairs? Or not?
Yeah, you can think of, you can break a Cooper pair and create two excitations. Yep. Yes?
Why does the Meissner effect break down when the applied magnetic field gets too strong?
So this, you can think of, this again, property of a material. So what you can think of is minimizing the free energy. So there is something we'll discuss later in the class today. So you can calculate the response a material has a property, say conductivity. So you apply a magnetic field. What needs to happen to expel all the magnetic field from the material is you need some inductive response. So you will have some supercurrent flowing that will oppose this magnetic field, and inside there are two magnetic fields, the external one and the one created by this induced current, and they cancel. Now, if you have a small magnetic field, this keeps happening. Now, if the strength of magnetic field, you keep increasing, the system will have, because of this induced current, the system will have some limitations. It's a property of the material, how much magnetic field it can withstand. So you can think of this as a material property. And after this magnetic field, the material simply does not have enough diamagnetic response to cancel the external magnetic field. So it must allow the magnetic field to pass, and you get the normal phase. But there are some superconductors, like type 2 superconductors, where there is an in-between phase where you have coexistence of vortices, which are normal pieces, where you have magnetic flux going through, and superconductor. So you can have some interesting phases in between regions. Any other questions? Okay, so last time what we did was to derive a formula for within linear response theory. We can write down deviation of expectation value of an operator, A, and we can write it down as an integral from t naught to infinity dt prime, the retarded correlation function of this operator with the perturbation h prime, and a convergence factor which selects the physical solution. This retarded correlation function is expectation value in the equilibrium state of the commutator of this operator written in interaction picture. So it does have the time dependence in the exponential due to h naught and the perturbation. Now you can write down this formula also in the frequency space, and that is typically used. So I can write down this quantity as an integral minus infinity to infinity d omega if you look at, so there are two terms in this commutator. You have expectation value with respect to equilibrium state before you turned on perturbation of two quantities, AH minus HA. If you look at each of them, this is nothing but, so this is calculated in the equilibrium. So you have e to power I h naught t a e to power minus I h naught t Now these ends, these are eigenstates of h naught. So this will just give you a phase factor. Similarly, this will just give you phase factor. So from this you can see that this is only a function of t minus t prime. So in general, this correlation function is only a function of t minus t prime. So you can write this, or let me just write it down here. So this correlation function so this one, you should really think of it So, okay, let's write this in frequency space. So there is no additional time dependence. So we are really talking about h prime omega here. So it could depend on, say, t prime, but then we integrate over t prime. So what we have just used is the fact that we are calculating expectation value in the equilibrium state. And just using that, we can show that this correlation function only depends on t minus t prime. And we can use that to simplify our Fourier transform. So this is in time domain, and this is in frequency domain. The reason that I'm still keeping t and t prime is because there are two time instants, t and t prime, and typically when you do the Fourier transform, you'll use one time variable. So what you can do is you can put this up here, and what you will find is that the Kubo formula can be written as an integral d omega over 2 pi e to power minus I omega t, t naught to infinity dt prime e to the power minus I omega plus I eta t prime minus t So we've just substituted this in this line. Now, this eta here, this convergence factor, in the end of your calculation, you will set eta to be 0, and in particular 0 plus, which is a small positive number. So your final results are not going to depend on eta. What we have really done when we inserted this convergence factor is we are artificially inducing a mechanism, a relaxation mechanism that chooses the physical ground state. Why? Because we want to keep only the physical solutions, which should not grow exponentially in time. So we assume that there is some physical mechanism, which we do not know yet, but that will kill the unphysical solution. And we just put this by hand, but in the end set eta to 0. Now, what we are going to do next, so this is an integral minus infinity to infinity. Next, what we are going to do is set this t naught to minus infinity. And what does that mean? We are not interested in transient behavior. So at time t naught, we turn on the perturbation. Before t naught, the system was in equilibrium. Now we are not interested in any transient behavior. So we are going to set t naught to minus infinity, and we are only interested in the response of system while the perturbation was present. So the response of system is calculated at time t, and the perturbation was turned on long time ago. Now here you can do change of variables, define t minus t prime as some variable t double prime. In this integral, you will get some minus signs, and in the end, using this, you can write that this quantity is minus infinity to infinity d omega over 2 pi e to the power minus I omega t So here we'll have one time variable and an integration over frequency, and we call that an integration over time, and we call that as the Fourier transform of this retarded correlation function. And in frequency space, you can simply write down delta AT as, so this is really, you can define this as the deviation from the equilibrium value of the response in frequency space. So where we have defined So what we are essentially doing is going to frequency representation, and this is sometimes useful, especially when we talk about AC and DC effects. Now, one of the most important experiments in condensed matter is typically you will apply an electric field and you will measure, or an electromagnetic field, and you will measure the response of the system to this externally applied field. Now, in condensed matter systems such as metals, insulators, superconductors, you will have a lot of charged particles. So when you have a lot of charged particles, what will happen is this external electric field or electromagnetic field that you apply, this will induce some currents in the system. So you have a system of charged particles, you apply some electromagnetic field, and as a response to this electromagnetic field, there is some current flowing in the system. And so you can write down the Kubo formula, the general linear response theory. The response of a system is proportional to the weak perturbation. So if the weak perturbation is this applied external electromagnetic field, the response will be some current density, and the proportionality constant is what we call conductivity. Next, what we are going to do is we are going to write down a microscopic formula for conductivity. How can we calculate this proportionality constant with just the knowledge of the system Hamiltonian? And we will use this formula. So in general, you can compare, this is what we want. Response is proportional to weak perturbation. And if this weak perturbation is electric field, then the response is some current density and the proportionality constant is sigma. We will generalize this in the following way. So we'll write down the response of the system, that is the current density defined by J, and this is now equal to integral dt prime dr prime sum over beta, and this is our conductivity tensor. So the proportionality constant in this case is conductivity, and we would like to calculate this conductivity by knowing the system Hamiltonian. Now, what we have assumed here, we have written a very general formula where we have assumed that the conductivity can be non-local. That means the response can be non-local. What that means is this current density calculated at some point R there can be a contribution coming from electric field at some point R prime. So this is just a general form of this conductivity. In some cases, especially if you have a system that is homogeneous, in those cases, you will find that this conductivity will be diagonal in position representation. But in general, it can be non-local. Yes?
So here we assume that we are in a non-relativistic regime.
No, so we are still in non-relativistic. So you can, don't worry about, I think these times you can also think that we will always talk about retarded correlation functions. So in causality is always, we don't have to worry about, so we do assume that the response preserves causality, and that is also an assumption. So we'll be only dealing with the retarded Green's functions. So next we know that from electrodynamics, this electric field this can be written as the scalar potential So if you're applying an electromagnetic field as perturbation, that means the system, you can write this electromagnetic field in terms of some scalar potential and some vector potential. So our goal next, so what we need to calculate this sigma, so this is a response of a system to an external magnetic field. We know we can calculate the response of a system if we know what is the weak perturbation and we know what this current operator is. We can calculate sigma. But at the moment we've written this down, we don't know how to write down this current operator. We can derive an operator for this current. And another thing that we need to calculate is how exactly this external potential and external vector potential enter the Hamiltonian as a perturbation. So we need to find coupling constants for these terms. Now, so next, let's try to find what is H prime. Now, due to the scalar potential, there will be a term in the Hamiltonian coming from the scalar potential which will be of type charge times the potential. This term you can write as minus E integral dr, the density R times phi external R of t. Now, these are single particle operators in the Hamiltonian. So what this is you can think of this as particle density, and we have multiplied this by minus E. So this gives you the charge density integrated over all space. So charge times the potential. Now, you can go through the standard procedure that we discussed in the first two lectures, write it down in second quantized notation, and you will find that this is same as minus E sum over sigma integral dr psi sigma r psi sigma r. So dagger psi So this is one contribution to our Hamiltonian, but there will be another contribution that will come from the vector potential. Now, this contribution from vector potential is slightly tricky to calculate. And what you will do here is, let's look at the kinetic energy term, and let's use minimal coupling. So what we can write is, so we know that there is this term in the perturbation Hamiltonian, but there should be a term corresponding to the vector potential. And the term corresponding to the vector potential will enter the Hamiltonian in the kinetic energy term. And this kinetic energy term, you can write as 1 over 2m sum over sigma integral dr psi sigma dagger r, the gradient operator minus the charge and the vector potential square. So next what you can do is, so what you're interested in is linear response. So look at terms that are linear with the vector potential, or A external. This term has two terms that are linear. One will be del dot A and one will be A dot del. integrate one of the terms by parts, and what we will end up, and there will be a term a square. So you can calculate this whole thing, and what you will find is that this term can be written as sum over sigma q h bar. So now what I'm writing is, let's say, h prime. So now what I'm writing is terms that are in addition to original kinetic energy. That is all the terms that have A in it. And this you can write as so we have this term in the Hamiltonian that depends on the scalar external potential, and this term that depends on the vector potential, external vector potential. Now you can use this relation in analytical mechanics, that if you calculate variation of the Hamiltonian function due to the variations in the vector potential, you can write this as minus q integral dr integral over space times current dot delta A. So variations in the Hamiltonian due to variations in the vector potential, using this relation, you can calculate what this current operator is. So this is one way of calculating current operator. You can also use continuity equation to calculate what current operator really is for a given Hamiltonian. In this case, you will find out, if you use this relation, you'll find out that there will be one contribution coming from this term, and there will be one contribution coming from this term. The contribution coming from this term is typically called as paramagnetic term, and the contribution from this term is called diamagnetic term. So you can write down the total current operator J So this is all of this term. So I will just write down, let's just write it down once. So this paramagnetic term, you can see, so let's write down with spins first. This is the paramagnetic term, and this is the diamagnetic term. So paramagnetic term involves gradient of the field operators, and the diamagnetic term involves the vector potential. Now you will note that the diamagnetic term is defined without a factor of 2. And when you take this variation in delta H, when you calculate delta H prime here, you will get 2A delta A, and that factor of 2 will cancel this 2. So this is really the definition of the current operator. Yes?
Is the current operator gauge invariance?
So yes, so when you will calculate the response, it should be gauge invariant. So you have the freedom to choose any gauge, and that's what we'll do next. We'll choose a gauge in which this phi external is 0. So H prime will only have terms corresponding to the external vector potential. So you can calculate conductivity in any gauge. It's up to you. But because we want, in this case, it's simpler to choose the gauge where external scalar potential is 0. So in this case, the external field, this is simply the time derivative of the external vector potential. And you can write it down as following. The external, now this is H prime. This is the charge integrated over dt, dr, e to the power I omega t, jr dot so we only have a contribution coming from the external vector potential now. Now you want to do linear response. So this is total current operator. The current operator itself has external vector potential in it. Now think of this, so the current operator has total vector potential in it. You can imagine that even before you turned on perturbation, there could be some vector potential before T naught. So in general, so in our notation, this A is A naught, which could be 0. You could have 0 vector potential to begin with, plus A external. So when you write down this current operator, and if you are only interested in linear response, you would only include A naught terms in the current operator. And you can go through the whole calculation. Next, what I'm going to do is, so this calculation is done in detail in the textbook. And please go ahead. I can send you a PDF of the whole calculation and go through all of the steps. What I'm going to do is write down the final answer. It's worth it to go through the calculation in detail at least once. What we will find is the following: that the expectation value of the current operator, this will be the retarded correlation function of the current operator with the external potential plus E over I omega m E external now. So this term really comes from the response of the current, and this term comes from the diamagnetic. So this really includes the paramagnetic term that has this current operator with the gradient, and the second term is the diamagnetic response of the system. So you can see this from this term. So because this is a square, you should really have a naught here. You should not have external potential, and this term simply becomes the density. So go through this calculation, and this will be the final result that you will find. Now in time domain, you can write down this retarded correlation function. So this correlation function involves H external. We know that H external involves J of R. So what you can do is, in this correlation function, replace this by the H external, and you can show that what really matters is retarded correlation function of current operator.
What does the superscript beta mean?
So this is XYZ, the direction. So for the moment, I am only I'm assuming. So this is just the external field is in beta direction, and this is just the current in beta direction before you applied the electric field. So let me write it down in the full form. So this JE alpha, so R omega. So you really have to compare this formula here with this. And I will just write down the result, and then we can discuss this result. So this is what we obtain for the expectation value of the current operator. And when we compare this with our definition for conductivity, we can see that this conductivity will have two terms, one coming from here and one coming from here. This term is really non-local. It involves two coordinates r and r prime, while this term only includes one coordinate r, and this term is local. So this calculation is done in detail in the textbook. So please go through it once. And what we'll do here is just to discuss this result in detail. Yes?
When we wrote the external field like that, was that the gauge choice, or are we just saying the external charge density is 0? Where did the gradient phi term
go? So we choose a gauge where the scalar potential is 0. So you can make a gauge transformation, so add two vector potentials, something that takes care of this. So I use the same notation for it, but I've chosen a gauge where there is no scalar potential. So the key point here is, if you look at this final result, there are a few take-home messages that we should talk about. In particular, one, you can see that this function, pi, is really a current correlation function. So what this function pi is, it's called polarizability. And this is really a retarded correlation function of two current densities. So what have we achieved in doing this calculation is, we have shown that you can calculate conductivity of a system starting with the Hamiltonian, and you can write it down as a retarded correlation function of a commutator. And in particular, if you're interested in conductivity, this you can use for any response within linear response theory. And if you want to calculate conductivity, there are going to be two terms, one coming from polarizability, which is a correlation function of two current density operators, and another term that is local in space, and that is coming from the diamagnetic current operator. Now, if you look at this operator pi, you can see there is minus I here. So this term is really real. This first term is real, while this term is really imaginary. Another thing that you can note here is what happens if you try to, so this conductivity is a function of frequency. What happens if you try to take the DC limit? So what DC limit means is setting frequency to 0. So you really have current that is constant in time, or field, external field that is constant in time. You can straight away see that this term here will diverge. So this term has a divergence in the DC limit when omega is 0. This divergence for normal metals and insulators is cancelled by a similar divergence coming from the paramagnetic term. And overall, you will have a finite conductivity. But in superconductors, this paramagnetic term simply vanishes. So for superconductors, if you calculate conductivity using this formalism, what you will find is that the conductivity is, for superconductors, is purely imaginary. Yes?
Why does it vanish for superconductors?
So you can see this in superconductors, you don't have these kind of operator. The current operator does not have these terms for single electrons. So to see this, what you should really do is do this whole formalism, but start with the BCS Hamiltonian. And there you will have Hamiltonian in terms of gamma operators. And so you can think of this, that paramagnetic term in superconductors will have both electrons and holes. So as a result of this, because you have both a paramagnetic term coming from electrons and a paramagnetic term coming from holes, it's one can expect that it's possible that the paramagnetic term cancels. But you can really show this by going through this algebra and replace the initial Hamiltonian with the mean field Hamiltonian in the BCS theory. So for superconductors, you really have an imaginary conductivity. Now, what does it mean? If you do have an imaginary conductivity, that means you will have no dissipation in the system. And this is what we see in experiments, that there is no dissipation in the system. Moreover, what we see is Meissner effect. So what this imaginary conductivity really means is that you have an inductive response. So if you apply a magnetic field, there will be an inductive response that will cancel this magnetic field, and you will have a perfect diamagnet.
For
Yes.
superconductors with an AC current, the conductivity is purely imaginary, but like not divergent.
Yes. So the AC response is slightly tricky. So what you have to worry about there is something called plasmons, which we didn't have time to go into yet, but you can think of this as follows. So if you have a finite frequency contribution, you can think of the fact that at corresponding to this, so say you have some frequency, so frequency is not zero, you have finite frequency. Corresponding to this frequency, you will have an energy scale, h bar omega. If this energy scale is again smaller than the superconducting gap, then you can expect most of what you know here to be true. But there is a regime when this frequency is larger than the superconducting gap, you can really start exciting quasi-particles. And that really changes, that will show up in this conductivity response also. So this formula is valid in general, and you can apply it for the AC case. So far what we did is discuss how we can calculate conductivity from first principles, or by just writing down the Hamiltonian of the system of many particles. We now have a formalism using which we can calculate conductivity. You can show similarly that you can also write down a formula for conductance. Now, conductance and conductivity are different quantities. Conductivity is defined as the ratio of the current density and the external magnetic field, external electric field. So you will write down J. So let's assume everything isotropic. You just have everything is scalar. J is sigma E. If you have a homogeneous system, then what you can do is you can write this J as the current I divided by the cross-section area. And this electric field you can think of as the applied voltage divided by some width. So you can really think of the system as following. So this is the width. So I should really call it length. So this is the length we are talking about. So you apply some potential difference. The electric field is given by this potential difference and the length. And from this, you can say that the current can be written as conductivity times area divided by length times the voltage. And now this ratio is defined as conductance. So conductance is a different quantity in the sense that it is not an intrinsic quantity. Conductivity is an intrinsic quantity. If you have many different samples of varying size and shapes, conductivity for all of them, if the material is same, is same. Conductivity is an intrinsic quantity. While conductance defined in this way, you can say it depends on area divided by length, so it really depends on the sample. Now, this simple calculation fails if you have a material that is inhomogeneous. And most of the materials in condensed matter system in the lab are actually inhomogeneous. You have some impurities, you have some imperfections that imply that conductivity is no longer a local function. So in general, if conductivity is non-local, this you can't simply multiply by area by length because the question will be which area. So in general, say your sample looks like this. So the question will be which area and which length. So what one should really do is derive a Kubo formula for current itself, for conductance itself. And you can go ahead and do that. And what you will find is similar to conductivity, which is a retarded correlation function of two current density operators. What you will find is that the conductance can also be calculated, but now it is given by retarded correlation function of two total current operators and not current densities. Similarly, you can use Kubo formula to define to find out what dielectric function looks like, and you will find that this Kubo formula for dielectric constant will include a retarded correlation function of charge density operator. And it is also in general non-local, and you can use, so this is a very powerful formalism, and you can use this to calculate various quantities that you can actually measure in the lab. So you write down your approximate theory given by this approximate, or what you think is the Hamiltonian of the system, and you can make predictions that can be tested in the lab. So next, what we are going to do is talk about quantum Hall effect, where you will make some prediction based on this formalism for, say, conductance. And what we will see is that sometimes we do see surprising behavior. And then we have to find out what is really going on, because sometimes this simple description, this linear response, might not agree with the experiments. That usually means that something more interesting is going on. And one particular example of this was quantum Hall effect, where the measured conductance or Hall resistance was quantized. So let's talk about that. Any questions before we move on? So this the short time that we spent on this linear response theory was to convince you that there is a straightforward formalism which you can use. Once you know the Hamiltonian of the system, you can use mean field theory to write down this description. But once you have the Hamiltonian of the system, you can calculate things like conductivity, conductance, dielectric response, and you can calculate it without any further approximations. From first principles, you can write down formula for these quantities in second quantized notation, and typically it will be given by an expectation value in equilibrium state of a commutator. And we also discussed that for superconductors, this response can be interesting in the sense that for superconductors, you might find that the conductivity is purely imaginary. So in general, these response functions will be complex, and the real and the imaginary part will have different physical meanings. So what I'm going to do is start with a simple experiment, which is imagine that you have some sample, say a wire or some piece of metal, something that has electrons, and you're applying some external current I. Let's choose our coordinates as following: x, y, and this is the direction z. Now, so you have applied an external current in x direction. What that means is that the flow of electrons is in minus x direction. So electrons in this sample are moving in this direction. So everybody agrees with me? It's just notation, how we define currents. So the flow of electrons is in direction opposite to the direction of current. Next, we are also assuming that there is an external magnetic field which is in the z direction. So due to this external field, now this electron is moving this way. There will be a Lorentz force exerted on this electron. So it's moving this way. The Lorentz force, because the charge is negative, it's out of the board. So this electron will get deflected due to Lorentz force in this direction. Any questions? Now this electron, it should move in this direction without magnetic field. That will give rise to a current in this direction. But in the presence of magnetic field, it should get deflected. But you can see that it cannot go very far in this direction. It gets deflected. So all bunch of electrons here will get deflected due to Lorentz force, but they can't go very far because the sample is finite. And they will start getting piled up on this edge of the sample. So they are going to get accumulated on this edge of the sample. When electrons get accumulated on this edge of the sample, you will be still left with some positive charge from the ions on the other edge. So you have also some positive charge on this edge, which is there because electrons from this side have moved on the other edge. Now, because of this accumulation of charge, this will generate an electric field. And this electric field will be in this direction, in the y direction. Now, this electric field will exert another force on the electrons. And the direction for this force will be opposite to the direction of the Lorentz force. So what is really happening? The electrons are flowing in the direction opposite to the current. They experience some Lorentz force due to external magnetic field. As a result, they get piled up on one edge of the sample. And as a result of this, there is a new electric field that builds up in the system, which opposes the motion of electrons that resulted in their piling up to begin with. So the electrons pile up, they create a new electric field, and that opposes their motion. And in equilibrium, the force exerted by this electric field will exactly cancel the Lorentz force. And as a result of this cancellation, electrons will have velocity only in the x direction. So in equilibrium, there is current flowing in the sample, and the current is flowing in x direction. And in equilibrium, the Lorentz force is cancelled by the force exerted by this electric field. So at equilibrium, you have this equation. So Vx now, I'm assuming, is the velocity of electrons along x direction. So everything here is the modulus, is a positive number. The directions are given in this figure. Any questions so far? Now we are going to define two voltages. So if current is flowing in this direction, you can measure, So we expect at equilibrium to be this electric field balances the Lorentz force. You can define two voltages. One we are going to call the longitudinal voltage. So this longitudinal voltage is because of this applied current. So there is some current flowing in x direction. That means there is some potential difference, and that is given by this longitudinal voltage, which we call VL along x direction. And we will define another voltage, which we call VH, the Hall voltage, which is defined as the voltage in the perpendicular direction. So what this VH is voltage due to this electric field EY. So this is just the definition. So from this, you can calculate the velocity of the electrons is simply EY divided by BZ. Now, this electric field in Y direction is really the Hall voltage divided by, now this I'm calling width, W. So where W is this width. So EY in general, for the simple case, you can write the Hall voltage divided by the width. The current I in x direction can be written as the current density in x direction times the cross section. Now, here we are going to assume that we have a two-dimensional system. So what we are going to assume now is that we have what is called 2D, which really just means two-dimensional electron gas. And you had a problem in the tutorial. You can create this using, in the lab, using various semiconductors, make a junction of, or a layered structure of semiconductors. Now, if you have a two-dimensional system, the cross-section is just the width. So Ix is the current density in this direction times the cross-sectional area, which is also the width W. Now, this Jx, the current density, you can write as the particle density or the carrier density N naught, which is number of electrons per unit volume, times the charge, times the velocity, times the width. And any questions so far? So this is all classical analysis. And when I put, now I'm going to define a quantity which I'm going to call Hall resistance that will combine all of this. So Hall resistance RH I will define this Hall resistance as the Hall voltage, which is voltage in y direction, divided by the current which is flowing in x direction. So this VH is EYW, and this IX is N0EVXW. Can cancel W. We know this Vx can be written as EYBZ. That will cancel EY, and what you will be left with is the magnetic field in Z direction divided by N0 E. Oh yeah, sorry. So the Hall resistance, you expect it to increase if you increase the magnetic field. Now, this is a classical prediction which was known from 19th century, and it has been verified numerous times in experiments. So it was really surprising when you do this experiment, you measure Hall response for a two-dimensional electron gas, and in 1980s, what they found is they increased the magnetic field, but the Hall resistance really was constant. So you expected the Hall resistance to increase if you increase the magnetic field, but it stayed constant. And now you can look at the graph that was distributed earlier. So if you look at this curve, you will see that the Hall resistance really has many plateaus. So we are plotting this as a function of magnetic field in Tesla. So you can see that it has many plateaus. So this is, please look at the graph that was handed over. Now, what they found is that this Hall resistance is actually given by H over some integer n e square, where n is some integer. This was the data that was measured by an experiment in 1980s by Klaus von Klitzing. And what this is called is integer quantum Hall effect. On this graph, what that corresponds to, the integer quantum Hall, corresponds to this plateau here at 1, and then a plateau at half, a plateau at 1/3, 1/4. All of this corresponds to n equal to 1, 2, 3, 4, and so on. So you have a plateau for integer values, n equal to 1, 2, 3, 4. So right now we are only talking about this part of the experimental data. And this is called integer quantum Hall effect because these values n are integers. So this was rather surprising because you expect this classically to be equal to this quantity, increased with magnetic field. Instead, what they found is a plateau, and not only that this was a plateau, it was also given by something completely independent of any other physical external quantities. It really just depends on the Planck constant h and the electronic charge. So this is something really fundamental. Because it includes H, you can expect that this is some quantum effect. So that's why it was called integer quantum Hall effect. Few years later, this was 1980s, few years later, they found out, they did some other experiments, and they found, so what they did was they did experiments at much higher magnetic field and samples which have less imperfections or less disorder, so much cleaner samples. And what they found is this n, this need not be an integer. This can also be a fraction. So where this is some rational number p over q, where p and q are now integers. In particular, they found that this, what they observed was this plateau here, 1/3. So the experiments, they show that this classically expected behavior is no longer, does not hold for two-dimensional electron gas. Instead, what you have is the Hall resistance is quantized, and it can have plateaus at some integer values of this n, and also at some fractional values, for fractional values times e square over h. Yes?
What was different about these experiments to previous experiments? Like previously, they had obviously measured a linear response.
So one was this, that this is strictly two-dimensional system. And another was that these are really much higher mobility. So you can think of the classical thing as just being a straight line here. And if you have a lot of imperfections, scatterings, then all these plateaus will get smeared away. Now, another important thing that was measured in experiments is when you try to measure Rxx, or the longitudinal resistance. So this just means, okay, so there, I will use this notation Rxx. This is just called resistance in the plot that was handed out. This resistance is defined as the ratio. So this voltage, the longitudinal voltage VL, is given by the longitudinal resistance Rxx times the current X. So this is really the resistance corresponding to the current in X direction and the voltage in X direction. What they observed is wherever you have plateaus, this longitudinal resistance actually goes to 0. So you can see in the graph corresponding to this 1/3, you have the resistance going to 0. And then you have a bunch of, so corresponding to these plateaus, at 1, for example, you have resistance going to 0. And for most of these plateaus, you find that the longitudinal resistance vanishes. What does that really mean? Is that when you are at these plateaus, so you can change magnetic field, but there is a window of magnetic field where Hall resistance is simply constant. When you are on that plateau, the longitudinal resistance is 0. That means the current flows in X direction without any resistance. Now, this is also surprising. You would expect various scattering, like if there are imperfections, you would expect that the electron is going to bump into, so you have cleaner samples, but there is still some disorder. It's not completely clean. There is still some imperfections. There are a lot of other electrons, and what you would expect is some finite resistance for the X direction, the current flowing in X direction. But what you find is that this longitudinal resistance vanishes at these plateaus. So what our goal is for next few lectures is to understand these features. First, it's relatively straightforward to understand this quantum Hall effect, and that is what we will do next. And what we will find is you can understand the quantum Hall effect by using a picture of Landau levels, include some disorder. So we'll do this in detail. And here, for integer quantum Hall effect, we are going to ignore electron-electron interactions. So we will only have single particle terms in the Hamiltonian, and using this Hamiltonian, we can explain all of these plateaus below 1. And then we will include electron-electron interactions in this two-dimensional electron gas, and using that, we can, or when we include electron-electron interactions, we can also understand some of these plateaus. So these fractions, there are many observed fractions till now. The first one that they found was really 1/3, and that actually has the easiest wave function. And so on. The list is ever growing. Now, there are some key aspects that I should mention before we do this in detail. One is, typically in condensed matter system, we can explain a phase transition using an order parameter. So there is some symmetry in the system that gets broken, and as a result of this broken symmetry, you have a new phase of matter. So before we knew quantum Hall effect, we thought that all condensed matter systems, all condensed matter phases can be understood by breaking of some external symmetry. Now, in this problem, this understanding was really questioned because all of these plateaus, they have same symmetry. You are not breaking any additional symmetry from going from one plateau to different plateau, but yet all of those plateaus are really different quantum state of the system. So what this problem did was it increased or it questioned our understanding based on this Landau theory of phase transition, which really assumes that you can consider an order parameter, something that is finite in one phase and is zero in other phase, and this order parameter is related to breaking of some symmetry. In this case, you can have a new state of matter, which is a new plateau, without breaking any symmetry. And this gave rise to the notion of topological order. So here all of them have same symmetry, but there is still different quantum state, and this you can classify as topological states of matter. Each plateau really corresponds to a different topological index and is and has a different ground state. Properties of these different plateaus can be very different from each other. Excitations can be very different. Effective charge of excitations can be very different. In particular, you will find that effective charge for the plateau at 1/3, the quasi-particles behave as if they have charge E over 3. So this is our goal for rest of the week. We are going to spend as much time as we can in understanding all of these complex features. Any questions? So we'll do this in detail tomorrow, and this was just a very quick introduction. You can go and read a bit more about it. There are still some plateaus that we don't really understand very well. So what I'm going to present is definitely not the complete picture. There is still some mysteries, and there's still some open problems in this field.